Okay, so I'd like to discuss Lagrange multipliers with you. It helps if you've watched the video titled An Application in Economics prior to watching this. It'll make things a little more understandable for you. So I recommend if you haven't watched that yet, go watch that first, then come back and watch this. Lagrange multipliers are a way of, or it's a procedure prescribed by Lagrange that helps us find the maximum or minimum values of a multivariable function with respect to some kind of constraint. So the example we looked at in the application economics video was we had two products, X and Y, that we were buying some bundle of, and we had what were called utility curves, levels of utility. So you could think of each level of utility as like an altitude. So along this curve here that I've just drawn, U equals 3, what that means is it's sort of like Z equals 3. And what we're saying is if you buy some combination of X and Y, this is say this is Y0 and X0, that's along this bundle, along this utility curve, then you would get 3 units of utility out of that, whatever units of utility are. I discussed that in the other video. It's sort of a strange thing. All right. So what did we do in that case? What we did was we said, hey, we had a budget constraint. We had a certain amount of income that we could spend. This thing had an equation. It was the price of X times the amount of X plus the price of Y, or unit of Y, I should say, times the amount of Y was less than or equal to the income I intended to spend on it. So we ended up with, it was a region, so to speak, of all the amount of or I should say all the combinations of X and Y that I could possibly purchase. All right, so having said that, we were looking for a way to get utility to be maximized. Now, we can see that there's probably some utility curve that comes through here and just skims by in one spot. And we were able to derive that we were interested in the point where the budget constraint, the slope of that, would be equal to the slope of the utility curve. So at this point right here, with this point of tangency, the slope of the budget constraint and the slope of the utility curve are the same, and we would get maximum utility, at least in the case of these particular utility curves, the way they're described. In some other cases, if I drew the picture slightly differently, it might end up giving me the minimum utility. But I'd still get an extreme value when the slope of the budget constraint and the slope of the utility curves were equal. Well, another way to say that, and basically the premise behind Lagrange multipliers is this. If you think about something called the gradient vector, so I was interested in the gradient of the utility function. The gradient vector is the vector that points in the direction of the maximum rate of increase of the function as I move along it. So if I pick any point. So right here, if I was interested in the gradient vector, it would look like this. And the other thing you could be sure of is the gradient vector ends up being perpendicular to the tangent line at that point. Well, the premise of Lagrange multipliers is pretty simple. It's saying that the gradient vector of the utility function, or the thing I'm trying to maximize, is equal to some constant times the gradient of the budget constraint. I'll call it B. So I'll just denote this as a function B of x, y is equal to income. Okay, or less than or equal to income. So what is this really saying? Well, we know that if we're saying two vectors are a scalar, one vector is a scalar multiple of another, I'll say it that way, then that means that the two vectors are parallel. And if they're parallel, then we're at a point where the tangent lines to the budget constraint and the utility curves are parallel. Now, Lagrange multipliers is more generalized than this. Clearly, I have a linear budget constraint here. You can see I've drawn a linear budget constraint. It doesn't have to be a linear budget constraint. It could be something curved, and you can have different utility curves and so forth. Here's the basic definition. It says to find the maximum values of some function f of x, y, z subject to a constraint, g of x, y, z is equal to a constant. You do the following. You find points where this equation holds, where the gradient of f is equal to some scalar multiple of the gradient of g. And we can write that in vector form. If you look at this thing here, here's the vector form of that equation, right? You can see that this component here would be lambda times that component, And then this component here would be lambda times that component. And then lastly, this component here would be lambda times that component. Okay? And then once you find points that work in that case, you evaluate the thing you're trying to maximize or minimize, this function here, which in our previous example was a utility function, at all the points from part A, at all these critical points we'll call them, I guess, and then you'd be good to go. All right. So I just want to look at this equation here that's in the blue box for a minute and say that there's another way to write that. We can write it this way, basically that following set of equations. Okay, so let's start a problem. Let's consider a problem. Let's pretend we're going to make a box that has no top, 4 sides, and a bottom. So you can see there's a bottom back there. Let's pretend its dimensions are x, y, and z. And we have 12 centimeters squared of material to use. And we want to maximize volume. That's what we're asking. And if you think about it, this screams like Lagrange multiplier. You're optimizing one volume or one quantity with respect to some restriction. We have a restricted amount of material. So we can write an equation for this. This is just area, surface area. We can say that the area of the bottom plus the area of the front and back, which would be 2xz, plus the area of the 2 sides, which would be 2yz, is equal to 12. And this is sort of like our g of function, or g of x, y, z is equal to k. Or in our case, k is 12. And we want to maximize volume. Volume equals x times y times z. So we want to maximize this function subject to that constraint. What we know then is that the gradient of v has to equal to the lambda times the gradient of g. Okay. So with some algebra and so forth, we can proceed. So the gradient of v, well, if we think about that, we're going to get vx equals, and that's going to be, if x is the variable, then the derivative is yz, vy. If y is the variable, then the derivative is xz, and vz, if z is the variable, then the derivative is xy. So this whole thing collectively is the gradient of v. The gradient of g, well, g sub x, if x is the variable, if you look at this expression, then we're going to have g sub x equals x plus 2z. And then this has no x variable in it, so it's a constant with respect to x, so that derivative is going to be 0. So we get the following. We get x plus 2z. So then gy is going to be, if y is the variable, then we get y0, we get x plus 2z. I'm fearful I made a mistake up there before. The derivative of, with respect to x, this would have been y plus 2z. Sorry about that. Okay. And then lastly, you're going to have g sub z equals 2x plus 2y. All right, great. So now we're ready to write our equations and proceed. So what do we know? We know that yz is equal to lambda times y plus 2z. And then we know that xz is equal to lambda times x plus 2z. And then we know that xy is equal to lambda times 2y plus 2x plus 2y. Okay. So here's the promise I can sort of make you. In each of these problems, the system of equations you end up yielding sometimes can be pretty, or usually is not very easy to solve or deal with. So you try and take advantage of symmetries or use algebra to re-express things, and hopefully something good happens. So you'll notice if I look at each of these things, it'd be nice if they're all the same, because then the 3 things on the right would all be equal to each other. And I'm going to be able to do that by multiplying the first one by x, multiply the second one by y, multiply the third one by z. And you end up getting these equations. X, y, z equals lambda times yx plus 2xz. And in the second case, you're going to have x, y, z equals lambda times xy plus 2xy, 2zy, sorry about that. And then you're going to have xyz equals lambda times 2zx plus 2zy. All right, so now you get that all these things are really the same. So I can start picking pairs. So I could take these two things and set them equal and end up with the following equation. Xy plus 2xz equals xy plus 2zy. And if you look carefully at that, some very nice things happen. These cancel. And if you look at the two pieces that remaining, you have the 2's that match, you have the z's that match. So together that implies that x must equal y. Well, that's sort of nice to know. All right, so that has to hold. Now I'll take these two equations, I guess. I'll take the second two. I'll take that equation with that equation, and I'll get that xy plus 2zy is equal to 2zx plus 2zy. And we'll see what we get from there. Well, actually, something pretty nice. These cancel away. And then if you look at what's left, the x's will cancel. And then you have y equals 2z. Well, take that together with this, and you end up with one nice equality. You know that x equals y equals 2z. All right? So if you look back in the other video about application economics, once you get the condition at which the maximum is going to occur, in that example, we were saying when the slope of the budget constraint and the slope of the utility curves were equal. In this case, what we're saying is if this fact happens here, then the gradient vectors are parallel. I'm going to take that condition and sub it into the constraint that I had. So if we go back up here, here's the constraint that we had. We're going to plug into that. Now, if you take the time to plug this in, you're going to do x equals y equals 2z. You plug these things in. For example, if you know that x and y are both equal to 2z, then you could put that here and here. You'll have 2z times 2z, or 4z squared. So it'll become 4z squared plus. And then if you proceed, if you go back here, and then you take, look at the second example, and say you plug in x, this piece, equals 2z here, you'll get 4z squared again. And then in the last case, you'll also get 4z squared equals 12. Well, that implies that z equals plus or minus 1 with a little bit of algebra. Now, z is representing a distance. Don't forget what this is a box, and z is the height of it. So it doesn't make sense for z to be negative, so z is positive 1. But that implies that x equals y equals 2. So there you go. So the volume's maximum value is going to occur when x is 2, y is 2, and z is 1, which is 4. Okay? Thanks for watching.